In this video, we are going to, at least in this playlist, we're going to look at lazy evaluation and Haskell. And the problem that we're going to play with is the insertion sort algorithm. And this is a code taken right from your lecture slides. And before getting into the specifics of lazy evaluation, actually the first part of the video, what I like to do is just get a feel for how exactly is this insertion sort working from a very, very high level. So if I look at the type signature here, the type signature for insertion sorters, it takes in a list of integers and it gives you back as an output a list of integers. Okay, this is straightforward. This is all understood because as an input, I need to pass in some kind of a list that needs to get sorted, and as an output, I'm going to get back the sorted version of that list there. So if I call iSort here, iSort on some list of integers, and let's say the list of integers here is 1, 6, 8, and 7. This is my input here, and the output over here is whatever is the sorted version of that list there. The way this algorithm works is that if my input is an empty list, the sorted version of the empty list is the empty list itself. Again, this is my base case, and it's something really, really trivial there. The recursive case here is that what I'm going to do is I'm going to first take this list here and break it up into two parts here. Let's say, or in this case, one over here, this one over here refers to my head. That's the head, and this piece over here refers to my tail. Okay, and more specifically, this head over here is basically just containing the value 1, and tail over here is basically a list. It's basically a list that contains 6, 8, and 7. Okay, now when I say tail here, I mean tail of this bigger list there, and when I say head here, I mean the head of that of this bigger list, which is contains a value 1. And the intuition here is I'm first going to sort the tail, and if I sort the tail, which is right here, I'm just going to sort the tail here. Okay, I'm calling iSort the insertion sort again on the tail there, where XS is basically my tail. If I call iSort on my tail there, and if this gets sorted, it's going to basically look like 6, 7, 8. Okay, and that gives you back a list there. Okay, so iSort on that list gives you back this list over there. And now the question here is, how am I going to insert the X? Meaning, how am I going to insert this one? How am I going to insert this one in that list there? Okay, so so that's basically the kind of the high level idea of what iSort does. But now the kind of question here is, how is this insertion going to work here? What are the specifics? How does this function get implemented? The implementation for insertion ins is basically it takes in an integer as an input. It then takes in a list of integers as a second input over here, and finally gives it back a list of integers there. So what insertion does, it says, okay, give me an integer, which is this one there, and give me this sorted list, or this list of integers, which is 6, 7, 8, and I'm going to somehow get this one inserted correctly in that sorted list, so that you now have this bigger or the larger list that also happens to be the sorted representation, with 1 being inserted into the smaller list there. Okay, so how do I do that now? Now, if I have X by itself, which is this 1 by itself there, and if I have an empty list, then, well, how am I going to insert X in the empty list? It's just basically the item itself in the empty list. That's my base case. That's my base case there. Okay, what's the recursion case here? The recursion case here is basically I'm going to do a little bit of pattern matching on this list that's being passed in, and I'm going to compare what this one is with that item in that list there. Now keep in mind that this piece is already sorted, right? This piece is already sorted. Okay, and this piece is already sorted. Then the insertion the way insertion works here is going to say, okay, look, let's compare 1 and 6 here, and if this one over here happens to be less than or equal to this value y there, I'm going to return back, I'm going to give back a new list. Remember, cons over here is the construction operator, where you create a list, where I'm going to give you back a new list that's going to be 1 cons, because in this context x is my 1, right, and y in this case is 6, and this condition is true. 6 is greater or equal to 1, and what I written back over here is basically 1 cons with y is basically 6 cons with whatever that list is, which is 7 comma 8. Now remember, I'm still haven't touched the lazy evaluation aspect of Haskell just yet. I'm just giving you a very, very high level idea of what this algorithm actually is doing. And then maybe later in my next part of the video, we're going to get into the specifics of how this gets implemented. So the output over here is going to be, because the cons is basically my right associative, this can be rewritten as 1, 6, 7, 8, right? It's the same thing. And this basically gives you back a list that is 1, 6, 7, and 8. So again, as the input that goes into that iSort, this list goes as an input to iSort, and what I get back as an output is this entire piece there, which happens to be the sorted representation of the input list. Okay, now what we're going to do now is we're going to, at least in the second part, look at the same problem. We're going to look at the same problem of iSort, but what I'm going to say now is we're going to find the minimum. We're going to find the minimum of the list. Okay, and to get the minimum of the list, we're going to kind of put an algorithm such that I'm just going to take the head of whatever is iSort of 1, 6, 8, and 7. Okay, so that's the expression that I'm going to look at in order to evaluate the minimum of a list of some numbers. Right now, at a very high level, if you're not familiar at least with lazy and eager evaluation, this might seem like a really inefficient algorithm, because I'm just going to go and sort this entire list there, and once the entire list has been sorted, I'm just going to take the first item from that list to give back the minimum of that list there. But using lazy evaluation, we're going to see some of the improvements that gets introduced, and we're going to see those nice little things and more specifics of lazy evaluation, at least in the second part of the video.